Hello viewers, this is Embedded Systems and Control. My name is Obiora Ezeaso, and this is the topic for today is going to be hardware design for a minimum build servo controller. This is a block diagram of a microcontroller with its peripheral connections. It was very necessary to draw this diagram so that I could be able to know how many configurable pins will be needed for the microcontroller. This will help me to select the correct microcontroller that has enough pins for my project. This is a detailed schematic of the servo controller for a DC motor which I have designed. It contains all the important ICs and their connections to the microprocessor. The IC1 is a microprocessor PIC 18F2420. IC2 is a motor driver. IC3 is for data transfer, is a serial EEPROM with the SPI interface. IC4 is also for serial port connection, which is for USB to RS232 COM. The encoder, the regulated power supply unit. The PIC18F2420 microprocessor is a microcontroller that has 28 configurable pins. It has a wide range of voltage, which ranges from 22 volts to 5.5 volts. This makes it suitable for pulse width modulation with its 16-bit performance timer. It does not require heatsink to switch the amount of current required for my project. And the MSSP peripheral connection allows for SPI interface. This is very important for speed in the transfer of data with and the MCLR port will allow me to be able to connect the ICD connector IC. The ICD connector will be used to debug the software developed in MPLab IDE, and it will be linked with the PIC3 or PIC2. And the version of my MPLab that is available to me will be compatible with this microprocessor, and I can simulate my project and through the serial port and monitor it in teraterms. So these are the reasons why I decided to choose this PIC18F24 because it's suitable for my project. The SPI located in the port C of the PIC18 is hardwired. The job of the SPI is to develop a synchronous communication method which transmits data received from the IOs to the microprocessor. The SPI allows the master device to communicate with the slave device by synchronizing the clock in the port SCK. It has a serial data output SDO and another port which is a serial data input. And also the master control block. The master controls the clock. If the buffer is full, a bit will be set to 1. Data will be stored in SBBF, and then it must be read before another byte can be exchanged. For the communication protocol, we use the FT232R integrated circuit, which allows USB to UART serial interface, and the UART has no master-slave communication sequence. Rather, baud rates are set up between the transmitter and the receiver. The speed of data transfer is set up in the internal clock of each of the device, unlike the SPI connection, SPI data transfer. So this is going to be very important for our teraterms to be able to synchronize with teraterms and monitor our project in teraterms. FT232 allows RS232 to USB port communication too. For the debugging, we have the ICD connector IC. ICD connector IC is going to be linked to the microprocessor through the MCLR ports. So the PK3 will be and PK2 will be connected to the ICD connector, and we'll use it to debug the program for debug the software for the project for the servo controller. The DRV8833 dual HP driver is a DC motor driver made by Texas Instruments. It allows for speed control and direction control, and it only requires 3 pins from the big microcontroller. Supply voltage for the motors, for the DC motors connected to it, ranges from 2.7 to 10.8 volts. But the nominal stalling voltage for the Mabuchi 500 DC motor that will be used for the project will only require 6 volts as nominal voltage and a nominal current of 0.35 amps. This motor driver is capable of supplying up to 2 amps. So for that reason, the double H bridge has been connected in parallel so that it can double its current capacity. And this is done so that if there's any need to put a bigger motor, a more powerful motor, it can have enough power to drive it. And the PWM speed control can be done from as little as 500 milliamp to 2 amp the current of output per H bridge. The Encoder Detector HLC2705 is an optical sensor. It is designed to sense speed and direction, and it has channel A and channel B. The speed is sensed by counting the pulses generated between the R and the holes of a rotary encoder wheel. My intention is to monitor the speed and the direction of the motor with this encoder. This is the optical encoder continued. Here's a typical setup for the optical encoder. Usually, you can use it as use channel A and channel B to monitor direction, and also use the tag to measure the speed. But it can also be used as quadrature encoder to produce 2 channels of pulses with 90 degrees shifting phase shift, and then this way you can monitor the speed and the direction. So, and then how it's done is that the motor is mounted on the encoder wheel is mounted on the shaft of the motor. So as the shaft of the motor rotates with the encoder wheel, it will be interrupting the beam which is mounted on the other side, the beam of the sensor, the IR sensor of the encoder, of the optical encoder. So the amount of time that it is interrupted is counted, and then it is transferred to the microprocessor. The microprocessor uses this to generate algorithm that will be used in the transfer function. Here we have a regulated power supply unit which I have designed. It supplies 9 volts DC, and also we can use a voltage divider is used to bring it down to 3.3 volts. So this 3.3 volts will be suitable for the ICs and also for the motor driver. But the motor driver that we have here tolerates up to 9 volts, so we can put 9 volts on the motor driver directly, and then we can use 6, and then we'll use 6 volts to give 6 volts to the motor. We'll program it to use 6 volts for the DC motor that was connected to it. This is a global block, a global architecture of hardware that will be required for this single channel DC motor, both for the building it and for debugging it and for monitoring. And this is where we end this is where I end this presentation, and I hope you enjoyed it. Thank you for listening.